Hello, good afternoon, good evening to some of you overseas, and welcome to RAT's 19th Technical Sessions webinar. There's a lot of familiar faces, which is great, and there's some new ones as well. Quite a few people are locally from Alberta here, but I see some people abroad, so welcome. And for those of you that are new to this series, just want to let you know, RATS was formed in 2004 as a social networking event in person, and there's a group in Calgary that does the same thing as well. We try to do the same thing in Fort McMurray. Never really got any traction. But in any case, we've started off with the Technical Sessions series in 2018 in Shore Park, and so now since 2020, we've been doing these things in online now. So with that benefit, we've been able to get people remotely, such as Craig, who's across the pond, and Ralph will introduce our speaker. Just also want to mention too that 2021 Calgary Pump Symposium, they're planning on putting on an event later on this year. Whether it's in person or virtual, well, I guess nobody really knows. So stay tuned for that. RATS also does a technical conference and workshop as well. They never got off the ground in 2020, but we will definitely be doing something either in person, hopefully by 2022. So anyways, I'm going to turn it over to Ralph, and thanks for joining us.
Yes, good morning, good afternoon, good evening, wherever you're connecting to us from. This COVID pandemic has moved us to this webinar format, but by that, it's also extended our reach, and we're pleased to be able to bring presenters from all over the place. So the intent of this webinars program is to be educational, and today we will be learning about torque meters from Craig Holmes. Just to let you know about upcoming event, next month in February, we'll be hearing from Burkhardt Compression, and they will be talking to us about compressor seals. So check with us. That will be February 18th. There is an attachment that will be showing up, and I guess that will be on our website after this presentation, and it is going to be information on torque meters. So just to not take any more time away from Craig, he's had a 30-year career in instrumentation, all of this in the industrial environment. He's worked for Shell and Air Products, and the last 8 years he's been at Torquemeters Limited. He's responsible for the global promotion of the Torquetronic brand of torque meters, and his emphasis has been on education and applications. He is in the UK from Northampton, and he has an honours degree in chemistry from the Nottingham University, and a global education, he says, in mechanical engineering from all of the rotating equipment engineers he's ever met. So thank you, Craig, and take it away.
Thank you. At least it didn't take me very long to get here. That's quite good. It's unusual. Hopefully you can see my screen. Can somebody tell me that you can? Excellent. Perfect. Right. So torque meters. We've been around for a long time. I won't bore you with too much, except that it was 1951 when we started, and we worked with a guy called Frank Whittle, who, if you're English, invented the jet engine. If you're American or other European, he didn't, but he was damn close either way. And what I tried to do is to give some information about torque meters and measurements of torque, some of the techniques, some of the technologies, and why you might choose a particular one over a different sort. I'll also talk a little bit about some of the things that can, well, let's just say some of the things that are worth thinking about before you decide what technology to use, and the best way of implementing the technology that you do use and things to look out for. We'll talk a little bit about why you might need a torque meter, and then we'll talk a little bit about novel technologies and why there aren't you know, 7, 8, 9, 10 different sorts of torque measurement devices, or at least technologies being used. As far as I know, there are only really 2 main ones, which are the ones we will focus on. Now, of course, I'm trying very, very hard not to be biased, and I'm sure if I do get to be too biased, you will pick me up on that, and in the questions at the end, hopefully somebody will say that I'm talking rubbish on a particular aspect, and I'd welcome that, because every day is a school day. So, what's a torque meter? It's an interesting question, and I've met people that only ever thought there was one type of torque meter. There are lots of different implementations of torque meter, but basically it's a device that measures the twisting motion of a driven shaft or a coupling under load. So basically, when a shaft is loaded, it twists. If you can measure that twist somehow and you know the speed, then you can accurately work out how much power is running through that shaft, and that informs on the driving machine and the driven machine. So in most instances, it's a power measurement device. It's independent of the OEM, and that can be useful. I have to be careful and diplomatic, as a good Englishman should be. The OEMs obviously have their own patches to protect, and the good thing about most torque measurement devices is they are independent of them, so you can have an interesting discussion with OEMs about the power that you're seeing or the power that's being used by a compressor or pump.
Greg, did you want to take this opportunity to run the poll?
Yes, I was going to say we did a fantastic pre-presentation planning and forgot to mention the poll.
There's always something. So I'll give you some time to answer the questions there, and once the activity dies down, then we'll get show you the results. Okay, we'll give it a few more seconds and we'll shut it down. Okay. Oh, 50% have heard of them. Not too many have used them. 10%. And a good amount, 15%. No idea what they are. So good spectrum.
That is good. That is good. And that also informs me that there'll be people there that can ask some really difficult questions. So that's slightly worrying. But hey, we'll cross that bridge if we come to it. Okay. Is my screen back up? Can we see my screen?
Yeah, the floor is yours again.
Yeah, thank you. So, types of technology. There are 2 main technologies. And when I said that they were the people that use torque meters as a measuring device with a small t, they generally think of them as all the same. This is where it gets interesting in that there are 2 main types. So there are strain gauges, which are very popular, and there are phase shift, which are, I would say, less popular, and there are reasons for that, which we'll come on to. So here is some pictures of strain gauges. They are basically a Wheatstone bridge arrangement, which is an electrical circuit with balanced resistance, which is adhered to a, let me get my highlighty pen. As you can see here, that's a Wheatstone bridge, and it's stuck to the inside of a coupling or a shaft. It can also be placed outside, and when the shaft is twisted under load, the resistance of the Wheatstone bridge arrangement changes, and what that means is you get an imbalance in the Wheatstone bridge, and that electrical imbalance is translated into a torque reading because the stiffness of the material is known. So the stiffness of this is known, and you can from that work out what the torque and therefore the power is. And it's a really interesting way of doing it. It's been around for a long time. We've used them for some of our aerospace applications, and it's a tried and trusted situation. So you can either fit it on the inside of the shaft, you can also put it on the outside. You need some other pieces of modification. but you can basically use the same coupling. And so that's basically how a strain gauge, what it looks like. There is a second type where you actually buy a complete flange that sits in line of your shaft and has the strain gauge already built in and calibrated, and you can get different flanges for different power measurements, and they're quite neat and tidy, and you don't have to mess around with doing anything to your own coupling if you're going for this sort of technology. So that works quite well. I'm sorry about this graphic, it's awful, but it does show some of the components, so I've sort of kept it in and tried to make it a bit bigger for you. It shows all the various components of a strain gauge. Because it's electronic and it's attached to the shaft, and this is shown on the outside, it could be on the inside. You have to get power to it, otherwise you get no signal. And so you have a coil around the outside that will generate by induction the power required to power the Wheatstone bridge, and also would take the signal back across to a control room somewhere. So there are a number of components, and that sort of will lead into some of the difficulties that I've encountered when people have used strain gauges, but we'll talk about that when we get there. The main benefits of strain gauges, there's one huge benefit, and it's that one. Compared to phase shift, it's cheap and cheerful. You can strain gauge a shaft for a few thousand US. You also can use the coupling that you have, or the shaft that you have, so you don't need to modify the running coupling in any way except to stick a strain gauge on it. And you can use it for torsional vibration measurements. Again, that's something that we see quite often these days, where you've had a shaft failure over time and you replace it, and then it goes again and you replace it, particularly on fans and stuff. And it's not that the shaft's been overloaded, and so the only suspect after eliminating everything else, bearing failures and the like, is torsional vibration, and putting a strain gauge on it will give you some good data as to exactly what's going on. So that's another benefit of strain gauges. And like all things, not everything in the garden is rosy, as we say in the UK. It has electronics that rotate with the shaft, so you've got to be a little bit careful about what your intention is. Why are you strain gauging it? What are you expecting to get out of it? How long are you going to be using it for? And that's quite important, because electronics rotating at any speed, 5,000–6,000 RPM, it's going to put stress on the components, both the components that power it and also the components of the Wheatstone bridge itself. So be careful of that. Also, once it's in, it's in. You generally speaking, depending on the application, you put a strain gauge on because you want to measure it when it's rotating. What you don't want to be doing forevermore is stopping it because you don't think it's right, and having to stop it and check the strain gauge or reapply it, and then have another go and get a different result, think, well, which was the right result? Was it the first one or the second one? You don't want to get into any of that. So you've got to be pretty sure of your installation before you start running. And that's the same with most instrumentation, I'm sure. If you're in the oil and gas or petrochem, or you're zoned as a class 1 div 1, then as far as I know, I've not seen a strain gauge that is class 1 div 1 compliant. If you're in a zone class 1 div 2, if it's a fan away or it's just a non-hazardous driving situation, then fine, the strain gauge could be used. But I know quite a few things like LNG plants, for example, they are class 1 div 1, and so you couldn't use a strain gauge even if you wanted to. And of course, the flange version is factory calibrated, which is fine in the factory, and it's only good in the factory if you can't check it once it's in the field. One of the big problems with strain gauges is that you can't really do any sort of checking of its calibration unless you take it off, and that's unless you stop the machine and then do some sort of checking of the install and some of the readings and some of the positioning. So it's not ideal from that point of view. The basic philosophy of a strain gauge is that you stick it on. It's glued on, and the degree of adhesion in a harsh environment, specifically oil and gas, but you know, if it's close to shore or any of those sorts of harsh environments, it's going to limit the adhesion for the strain gauge over time. So you can, these are things you've got to be aware of, and there are lots of situations that actually these aren't issues, and in those situations strain gauges are a really good option, and I'll have a table later on that shows where you should and where you shouldn't perhaps use each of the different sorts of technologies. So that's strain gauges. Phase shift. Now phase shift is basically, from my experience, and I'd love to be told that I'm wrong, but from my experience, phase shift is, there are two different ways of doing it. You do a monopole or you do a torquetronic. Now a monopole basically is this system, which is basically Copflex. If you're familiar with Copflex as a Regal Beloit coupling brand, they have a very good phase shift torquemeter device. And again, it still works on the principle of twisting of the shaft, but rather than the shaft twisting and having something stuck on the shaft, there are wheels that are fixed to the shaft at 2 points, and then they're brought together in a mesh configuration, as you can see down here. And then as those wheels then offset under load, that's where you get your measurement from. And these changes in phase are picked up by two monopole sensors. They're passive variable reluctance sensors. Generally you have two at 180 degrees to help with alignment issues. So that's one. The second one is Torquetronic, and that's the one that we do at Torquemeters Limited, and we've been doing that since about 1974. So there isn't anything new or sexy about this. I'd love to say it was, but it isn't. It's basically a slight modification of the coupling, which you can probably see there's a tooth wheel here and a tooth wheel here, and everything else is the same, and the coupling guard is manufactured by Torquetronic. So signals are generated inside these coils here, which I'll show you in a moment on the next slide, and then those signals go to a decoder, either in a control room or locally mounted. So this is how the signals are basically derived. Both methods use the fact that sine waves are picked up when teeth cut through the sensing area, either the probe here or through the magnetic field that's generated by coils. So there's a coil inside the coupling guard above the teeth at a space distance to allow for enough twist. And as you then twist, these sine waves that are generated here from these and these and from these and these become phase shifted. And both the couplings in both these systems are calibrated so that the stiffness is known. And if you know how much they've moved and you know how stiff it is, you can then derive the power reading. So that's the main difference. You've got physical manifestation of twist in the metal itself moving on a phase shift device, and you've got something that is stuck to the shaft or coupling spacer that provides signal on a strain gauge. So just like we talked about on strain gauges, a little bit about the operating benefits of phase shift. So for a monopole, there are no...
I just want to, Ralph here, I want to interrupt for our audience just to let them know that they can submit questions via the chat or the question, the toolbar. So yeah, we'll have time afterwards for reviewing those questions.
Okay, we forgot to tell them that, didn't we? Oh dear.
Yeah, that's my fault.
That's okay. That's okay. I thought I'd done something wrong. I thought you were going to say, what are you talking about? Anyway, so operating benefits of phase shift on the monopole, because you're taking readings based on the shaft, there are no electronics on the shaft to worry about. It's a direct measurement of the coupling twist. Because there are no electronics on the shaft, you can do class 1 div 1, and because it's just the metal moving, in general harsh environments are okay. So that's one of the main differences between the two technologies. Similarly with the Tortronic system, the first 4 are exactly the same. Tortronic goes a bit further in that it will replace completely the coupling guard and has the ability to give a calibration check in situ. And it will do torsional vibration, whereas the monopole phase shift won't. And there are a couple of other additional benefits. So you could have a SIL2, which is safety integrity level. So you can use it as part of a functionally safe system as a control device. Basically, it's a redundant system, so it's 3 torque meters in one. So if one fails, you've still got backup readings. And also, Tortronic generally will do a temperature study to tell you what windage is going to do to your coupling guard environment. So those are the sort of main benefits. But of course, like all things, it's not a panacea. There are things to be aware of. On the monopole, if you remember from the drawing, there are two probes, and they are supplied in a box for you to install as a user, or the OEM will install them. And the alignment of those, they are basically you have to weld a boss onto the coupling guard with a threaded hole, and then you have to align the probe using feeler gauges, and there are certain tolerances. And it's perfectly fine. There's nothing wrong with doing that, but it's something you have to be aware of. You can't just chuck the monopole sensors in and think, yeah, job done. There has to be alignment checks. And of course, there isn't really a way to check calibration with that system, not that I'm aware of. Again, it's a good system, and I've spoken to Copflex about calibration, and their answer is, well, it doesn't need calibrating because it's based on the movement of metal. And as an argument, that's fine. But I know I've seen people with clipboards with they need to tick a box to say it's been calibrated, and so being able to do a check is a useful thing. It also forms an additional section of the coupling guard because of the coupling, sorry, because it's a drop-in section. Also, cost compared to strain gauges, it's more expensive. Because there's more to it, really. And you can't do torsional vibration with the monopole system. With the Tortronic, I suppose the main difference is it's a major engineering solution. So having to be involved with the coupling guard and how it connects to the driving and driven machines, all of these things add up to a bit more commitment from either the end user if it's a retrofit, or from the OEMs. If you need to know where the compressor case is compared to the shaft end, normally nobody cares. But for the Tortronic system, because it's completely the whole guard, it has to fit between the two machines, and so all of that information needs to be known at the design stage. So there's a bit more involved. The alignment of the coupling guard is crucial. So normally a coupling guard, you just hammer it on with a big hammer. As long as it covers the coupling, you're fine. But with the Tortronic system, it has to be aligned using feeler gauges to get the best out of it. Of all the systems, the Tortronic is the most expensive. So that's obviously a thing to be aware of. And quite often there'll be cross-site cables to go to a control room. And I'm constantly amazed how often those cross-site cables are not connected up correctly. I mean, there's only 4 of them, but you'd be surprised. You get coil A will go to coil B and the control room, and even though we label them. But anyway, that's by the by. So there are things to be aware of. So how do you decide which one is right for your application? And there isn't a yes or no answer to this, but some of the criteria you need to think about is, what are you going to do with it and how long do you need it to work for? So if you're going to be using it, say, for process control, if you're feeding back the power reading because it's going to control something, then I would say a strain gauge isn't a long-term solution for that, whereas both the phase shift technologies will be. And that leads into continuous duty. If you're looking to continuously monitor over the lifetime of the plant what's going on in terms of power delivery, then a strain gauge is not going to be good for 7, 8, 9 years. It's, you know, we've at Torquetronic, I've seen strain gauges fail after 6 months, and that's just because it probably wasn't attached properly. But you know, it isn't good for long-term use. Conversely, acceptance tests it's a great place for strain gauges. You know, if an OEM has got to deliver a certain amount of power to the end user and they want it to be shown rather than calculated, then you can put a strain gauge on the shaft, start the machinery up, and say, there you go, there's your reading. And then what happens after that doesn't matter. And that's a big market. Service support is an interesting one. Can you do any diagnostics on site? So if you have a problem with the reading or you don't like the reading, can you do anything about it? And I think with strain gauges, and okay, I'm biased, but with strain gauges and with monopole, it is difficult because there's nothing to interrogate. With a Torquetronic system, you can do various diagnostics because you've got a powered coil inside the coupling guard, which should have certain parameters which can be checked. So if all those check out and the twist is as it always is, because you can't change that, then you will have good readings. And that's quite nice for end users to know. Design longevity is more to do with how long has it been designed to be used for? You know, is it just well, let's just see what's going on for now, or is it, well, we want this to go on for years for the life of the plant? Again, strain gauge is not so much, phase shift definitely so. Repeatability. So this comes down to what might change over time, and things like the movement of the adhesive or the power going to the Wheatstone bridge arrangement on the strain gauge. They're all question marks in my mind, in my experience. So I would say, look, you know, if you want something that's going to be repeatable, or you want to compare, you know, say you've got 3 shafts doing the same duty and you want to do them all, then I think a phase shift is a better way of doing it because you've got more consistency there. We touched on hazardous areas, and monopole and the Torquetronic will be fine in Div 1. The other thing that I think is important is you've got to bear in mind, where is this instrument going to go? It's going in a nice clean, let's say a nice clean compressor station where you've got good ventilation, it's always warm, it's a constant temperature. Well, then you could see a strain gauge might be okay, as long as you weren't planning to use it for you know, years and years and years, but it would be okay. But if it's in an oily, dirty environment in the backyard of Texas, where you have hurricanes and all sorts of nonsense going on, then you don't really need something derived from a laboratory. You need something that's a bit more industrial, and I think phase shift fits that bill. But of course, it's all very well me saying that, you know, you should go for these more reliable, more user-friendly, more controllable solutions that will last forever, but they cost probably 3-4 times the cost of a strain gauge system. So it may well be that strain gauge is the only option because that's the only budget you've got, and we get that, and we understand that. It doesn't change any of the facts, but it is sometimes pretty major implication. The other issue that sometimes arises is the need for a spare coupling. If you need a spare coupling on a duty, then do you need a spare torque meter as well? If it's continuous duty, I'm thinking here, and you would need a strain gauge, a new coupling. You would need a new insert for a monopole, but with the Torquetronic system, you wouldn't need a spare torque meter. You would just calibrate the spare coupling. So that's what I would say, things to think about, and when you're choosing to measure the power accurately. The other one I haven't put on there, of course, is calculations. You can calculate what should be the right power, but I think that's for a different day, because there's lots of reasons why that gives such a margin for error that it suits everybody but doesn't actually tell you very much. But we won't talk about that. So, okay, so we'll talk about installation and some of the things to be aware of. The key with strain gauges is adhesion. Make sure it's on the shaft properly, because if it isn't, then you get duff readings and that makes things worse. For monopole, the position of the on-guard sensors to allow for correct thermal growth, that's the key, because if you move away from the optimum position, changes the values, and that's not really what you want. And it's all detailed very clearly in Kopflex's literature, but it is something to be aware of. The other thing that I've found is that quite often, well, always in fact, the installation is handled by the OEM, or it's handled by yourselves as a site operative. It's not handled by the manufacturer of the equipment. So you've got to then organise correct positioning of the bosses that the sensors go through, and also the correct alignment. And that's similar with the Tortronic. You've got cross-site wiring, which I mentioned before, which amazes me how people get it wrong. But also you've got the mechanical alignment that you need to be very careful of, because again, if you don't get that correct, you'll get readings that don't make any sense. So calibration is the other thing that I'd like to talk about briefly before we get on to why would anybody be bothered to measure. So once it's on the shaft, strain gauges are difficult to calibrate. You've really got to stop the shaft from rotating and take some measurements. Monopole phase shift, it's really only a factory calibration because you don't need one apparently. And Tortronic system, you can do an on-site roll-down check, which is basically a simulation of something that we do in our factory, but you can do it on site to check that the zero is okay. And that's quite useful as a diagnostic tool, as well as being able to check the calibration. So why on earth does anybody want the torque meter? Excuse me, I'm going to have some gin.
Yeah, we're 33 minutes past the hour, Craig.
Yep. Okay. Well, we're fine, I think. So why would you use one? Let's do this. Let's get all this on. Okay, so you would use them because you want to make sure that all the money you're spending on fuel as a gas turbine or a steam turbine, that all of that money is giving you useful work, either in a pump or a compressor or whatever. So being able to run it as efficiently as possible is the key. If you've got a gas turbine, then the figures speak for themselves. If you've got a steam turbine, then you've got lots of complications because of the water quality and the consumption tables, and you've got no real way of knowing quite often what's going on in terms of power delivery. And so a torque meter is a really good solution. Generally, a lot of money is spent on washing machines, compressors and turbines especially. And having a torque meter gives you data as to when you should do it, and perhaps more importantly, when you don't need to. It also will give you an idea of, having washed, how much power do you get back? Was that, $10,000 US or whatever Canadian equivalent is, was that worth spending to get the increase in performance that we've got after washing? So all this is to do with maintenance costs, and this is my favorite slide in the world-ish. So why would you measure? And on the screen now, you've got two identical scenarios where you've got a turbine driving a compressor, and for the same amount of fuel, you get less work over time. And they both look identical. So if you have a torque meter coupling in between, and the torque meter is reading this, then you know that the power in the shaft is decreasing. And so the compressor is doing whatever it should be doing with the power it's being given, and it's the turbine that has suffered a degradation over time. Similarly, if you put a torque meter coupling in this one and the torque meter is showing this, so stable, then it's all of the power from the driving machine is going into the compressor, and it's the compressor that you need to look at. So that gives an idea of why it's useful. The other thing people use it is for compressor mapping, and I'll run through this quite quickly. So if you've got 16 megawatt turbine in this case, which is what it was, and you try and map it down onto the efficiency island here, but the separation of these red lines gives you an idea of the accuracy. You're not quite sure. It won't be exactly 16 megawatts. So you're mapping it somewhere down here, but you've got your surge line here, so you don't want it to go over here. So you map it, and you could be over here somewhere, and that's not super efficient. And that's all to do with the inaccuracy in this value. Whereas if you have a torque meter, you get a much more accurate power measurement, typically 1% accuracy. And so you can map straight down onto your efficiency island, and that gives you much more of a warm feeling that you're getting the most out of all the assets that you've spent money on. So that gives an idea of some of the things people do and why it's used. In general, when we speak to end users and we say, look, you know, you've got torque meters, what are you doing with them? Why are they so fantastic? Why do you love them so much? And the most popular answer is data. You know, it gives them data and accurate data, and it means they can make good decisions on that data. So now we're going to talk a little bit about novel methods, and some of these we've got experience of at Torquetronic. Some of them I've seen touted, but I've not really seen many used, apart from this one's been around for a long time, and that's probably not very good on the screen, but it's zebra tape and an optical probe, and you basically stick the zebra tape around the shaft, and using an optical sensor you can get a strobe effect which gives you feedback on torque, and that's fine in theory. The issue is you have to get it aligned correctly, you've got to get the ends of the zebra tape correct, and it has to stay clean. So for a quick check, yeah, I've seen them used and they are okay, but it is a bit of a faff, as we say, to get it lined up properly and to get it to work as it should. So from here on in, some of these I've seen touted, and they are variations on a theme, all of them pretty much. So a surface acoustic wave is basically a frequency-based strain gauge based on a quartz substrate. So rather than a Wheatstone bridge being stuck onto a shaft, you stick quartz substrate onto a shaft which then rotates, and in the same way as a strain gauge, you power it and you get a similar sort of response. And so it suffers from some of the drawbacks of strain gauges, and to my mind, I don't really see any benefits of this as opposed to using a strain gauge. So it's just another variation. There is also various versions of optical strobe based, and this was another one that I've not seen, but I thought it looked interesting. You strobe one wheel whilst measuring from another wheel, and any twist shown on the strobing is taken back to the sensor on the first wheel, and then that gives you an idea of what's happened to the twist, and from that twist you can then measure torque. This one got me very excited, almost excited as the last one, which we'll get to in a moment. But this was basically magnetizing a section of the coupling or the shaft and using the inherent magnetism in that as a way of detecting twist. In theory, fine. The problem with magnetism is it's a strange beast. It is an exact science, but in the real world, it is influenced by other metals that are around it, other ferrous metals, and we at Torquetronic have some experience of the way magnetism can affect our magnetic coils. So I'm not surprised it's not very popular, although on paper it looks really interesting. So another version of a mechanical optical similar to the monopole is the mechanical optical one you see there, and that shows two points being taken on the shaft, and they are, they will twist in the same way, and you have an optical sensor which reads the scale based on what's placed on the torsion strip. I've not seen this one. I don't know if it's ever been used. The final but one, penultimate, they say, is the optical paint. And the idea of a torquemeter that you paint onto a shaft is the holy grail. But to get that to work, it's a mechanoluminescent paint. And so you're involved in light again, and you've got to keep it clean. And industrial environments don't lend themselves to cleanliness, I've found. And so in the laboratory, fine. In the real world, maybe not so fine. And finally, this is something that Torquetronic looked at, and it illustrates that, we're not just sitting around twiddling our thumbs waiting for orders to come in. Although we do just that some of the time, and we are actively looking at better ways of doing it, and we came up with this laser slotted disc technology, which isn't anything new and exciting, but it's put together in a way that hasn't been done before, and we got it to prototype stage, and we got some good results. And like a lot of these things, it ends up going to that point because that's all in-house, but then we wanted to try and roll it out to a tame end user, and that's when it gets really difficult, because end users are busy doing their thing, and the proof of all of these technologies is always at the end user. So that's what I wanted to talk about. There are some further reading if you're interested on the different technologies, and that's me done, really. So thank you if you're still there. I'm sure you are. And any questions, I'm more than happy to try and answer them.
Thank you, Craig. Ralph here again. Turn my camera on. While we're waiting for questions to come in, I have a question. What about adapting for an existing machine? You have a driver and a driven unit. How do you add a torque meter into that system so that you know what's happening in your process?
Yeah, the best way, I would say, is a strain gauge, because you can use what you've got, and you just put a strain gauge on the shaft, and then away you go. So if you're, again, it comes back to what are you looking to do? Why are you needing to measure? If it is because you think, well, what's going on at a particular point in time, then a strain gauge is the way to go for that, without any doubt. If you're thinking, well, we really want to know over a longer period of time, then it's more of an engineering project. So if it was Torquetronic, we would need to know what the coupling looked like that was in there, because we'd need to swap some of that out because it won't have our signal teeth on it. So it would become more of a, well, it'll be more expensive, but it's more of an involved engineering study in that situation. And the same with, if it was the monopole phase shift, you would need to change the spacer shaft and drop in a new spacer with a power wheel configuration to give you that twisting of teeth. So it does come back to, what are we trying to achieve with the measurement in pretty much all the cases, rather than we need a torque meter. That shouldn't be your first question. Your first question should be, what are we trying to achieve with measuring the torque? Is it 10 years down the line we want to measure the performance of the steam turbine? If that's the case, don't go for a strain gauge. But and even for a retrofit, I wouldn't put a strain gauge on it.
Comment on the strain gauge version. I've seen a strain gauge where the power was supplied by a 9-volt battery strapped to the shaft.
Yeah.
Any comments on that?
Well, good luck. I don't know what speed a 9-volt battery would achieve if it flew off the shaft. It depends on the speed of rotation. It's like all these things. If you strap a 9-volt battery onto a shaft, if you put it on with something sticky enough to overcome any centrifugal forces, then it'll stay there. And how fast is it going? Does it unbalance the shaft? How long is it going to be there for? Again, it may well be that if you're in a situation where you're just wanting to measure something and you've got the opportunity of starting, stopping, then, you know, put a 9-volt battery on and power it from that, run it, stop it, got your results, take it off, job done. So I'm not suggesting that it's a silly idea. It isn't. It's just horses for courses. So, you know, I'd stand well back, but it is doable.
Yeah. Further on that, of course, the step up is the device that induces the voltage to the electronics that are rotating on the shaft. So that I have seen and needs a pretty good system to align the rotating collar to the static collar. There can't be much shaft movement, nor movement of the static collar has to be very well rigidly held in place. If everything's shaking and moving, that's not going to work. Do you have any comments there?
Yeah, I mean, because I work for Torquemeters Limited and we do Torquetronic, I did try and keep it balanced in terms of not really having too much of a go at strain gauges, but there are inherent issues with when you're strapping stuff to a shaft, and once it's there, it's there. So it's fine if it's done right. It's like most things, you know, it's fine if it's done right. And there are lots of companies in North America that will go and they'll come and do it for you, and you hire them and they'll come in and they'll strain gauge a shaft for you, you know, and they do a fantastic job. And I don't want people to get the impression that phase shift is brilliant and strain gauges are rubbish, because that's not true. But again, it comes back to what are you trying to do and how much money you've got to spend and when do you need it doing, and they are key. So yeah, be careful when you strap stuff on for things like balancing and alignment. I think all of them have a key requirement for alignment. So yeah, you've got to be aware of that.
There's a question there, Andrew. I'm having trouble reading it in my screen.
So basically, Chris Casey's asking about, you know, for instance, something with a 3-inch shaft. So, you know, you can kind of get you know, an order of magnitude of what kind of power that would be, but, you know, just he's wondering about the cost implications. And then I'm assuming he's talking about the phase shift system in particular.
Yeah. So if you're talking about a 3-inch shaft, he's talking length or diameter. I presume if you diameter. Okay. Well, the key thing for phase shift is over the amount of available shaft between the two sensing points, you need to have enough twist. So if it's a 1-inch shaft, as long as you've got enough separation. Now there are other issues. If it's really thin and you have to put wheels on it, then you're changing the mass, and you've got you still got to do all of those. I mean, one of the disadvantages of phase shift is you've got to modify the coupling. You know, that's one of the big things, because you've got to put teeth on it, and they have to be in a position that gives enough twist. So for the Torquetronic brand, that's definitely true. For the Copflex phase shift, there's a bit more flexibility because they generally bring their wheels where they do the detection as a drop-in section. And historically, they've been able to do more small installations than perhaps Torquetronic has. But it is, you know, even if it's obviously if it's a solid 3-inch shaft, then that's fine. It's all to do with the amount of twist. So until we see a coupling, generally speaking, the way it works is whenever we get a request to have a look at something, the thing that I always say is, what's the coupling look like? Because that generally defines where the machines are on either end. You know, if it's a retrofit, they ain't going to move the machines for you. So unless they're really, really kind. So you're left with the length that you have with the machines and the coupling in between, and that's what you have to work with. So yeah, it's doable.
Okay, so Hari Sarkar is online. He wasn't able to type it in, so maybe I'm just going to unmute him and just see if you'll have to unmute yourself too there, and then because you're self-muted, and then you can ask your question.
Hi, Andrew, can you hear me?
Excellent. Yes. Afternoon.
Okay. First of all, I will give thanks to speaker and all the attendees, because you guys, this is the first time I'm attending, and I had a little bit trouble in adjusting the application to get how to like to get access for asking question and all this stuff. That's fine. Next time I'll fix it and sit with the human, and I'll get be Excel. So very interesting thing. My takeaway from this instrument, from this application is like that in my world, I'm a reliability engineer for rotating machines. So in my world, I see that say a turbine or a gas turbine or a steam turbine or a compressor is driven by a electric motor. So it is very important to know that how much the driver is transferring power to the compressor. Because if I want to do a diagnosis of the transfer of rated power throughout the mechanical train, like the driver, gearbox, and then the compressor shaft, and then the process parameters. If I want to do a check of individual, then this strain gauge will help me to quantify how much power is being transferred by which shaft. Correct me if I'm wrong. So
No, absolutely.
This is very useful in my world for the troubleshooting and diagnosis of the rotating machines. Only thing I'm struggling to understand, like if it is so complicated to install, and if there are so variables which may contribute to the accuracy of the machine, like you are talking about, you mentioned alignment issue is one of the things, and the complexity of installation, that will not be very much user friendly to me. Rather, I would say, yeah, go ahead.
Yeah, I mean, I point out some of the issues, and they are very popular. Strain gauges are very popular ways of measuring power in a shaft, and they don't become popular by being rubbish. All I've tried to do is to say, look, if you're going to use a strain gauge, these are some of the things you should be aware of, and if any sensible, well-trained and supervised engineer should be able to install a strain gauge if the system is provided with all the right documentation. So it isn't inherently difficult. There are just, it's particular, I would say, rather than difficult. So just make sure that all of the things are correct. If you were just to rock up on site with some double-sided tape and a strain gauge and took the coupling guard off and chucked it on, it wouldn't work. But if you got to site and you had the right equipment and the shaft was clean and everything was installed properly, you'll be fine. And it's finding a balance between those two extremes to get good data. So that's what I would say. There would, if you want to know just at that moment what's going on each shaft between the machine casings, if you've got quite a long drive, then yeah, absolutely. If you want to look at gearbox losses, then fine, yeah, put a strain gauge on. If you want to look at gearbox losses over a long period of time, don't put a strain gauge on. Use a phase shift device, because that will be better for longer.
Okay, excellent. So I just want to bring one example. I did, like we had a driver, variable speed driver, VFD, driving a cooling tower pump, and I invited probably GE, and they put just a piece of they stick a piece of metal or piece of electronics on the shaft by screwing or by just adhesives, I don't remember, and then remotely the data was gathered and then the data was analyzed. So is it similar thing like pole, the monopole you were talking about?
No, that sounds like a strain gauge to me.
Yeah.
If they're sticking something on the shaft, then that's definitely a strain gauge. Did it give you what you needed?
Yeah, they gave us the whole purpose of this job was to see how much, whether the rated power is being transferred to the pump, because the pump was not performing what it should. So the diagnosis, the strategy was to see how much power is transferred by the driver. So what I am trying to focus here, my point is here, that was very user friendly. Like you put a piece of electronics and which does not fly away, and then sitting nearby from the Wi-Fi or Bluetooth device, all the data were collected during this whole running time, say 1 hour. So this type of thing is very user friendly in the industrial world.
Very good. Yeah, you know, if it works, fine, absolutely, and that's just the sort of application where a strain gauge is really useful.
But your one, the one you are showing today, these two strain gauges, it looks to me that the second one, which gives more accurate data, has got a lot of wirings and harnessing into the shaft. Like this is something one plant engineer or plant business or leadership will not want to like. We will not be very much happy to do those types of things in the shaft.
Yeah, maybe GE have a more novel approach, or they have a packaged strain gauge with the electronics, and it looks like it's all in one package. And I mean, you know, the pictures that I showed, they were not a panacea for all strain gauges, but the philosophy still stands that they had to stick that on, and GE know how to do this because they've done it many times, and because you've got good people doing it, you got good results, and that's fine, absolutely fine.
Okay, so I was thinking that the one which you are presenting today, like, did I understand correctly that it is very user friendly, like that type, or it needs to complete disassembly of the coupling hub, and you need to mechanically install this gauge, or you need to harness a couple of things, and then, so that was my.
Yeah, I mean, it's difficult without actually seeing how GE have done it. You know, in general, the signal has to be picked up from somewhere, and it has to be generated from something with some sort of power. So if they have a novel way of doing that, they've kept it very quiet, and I'd be very delighted to learn about it. So I will, after this, well, actually probably not after this because it's 8 p.m, but tomorrow when I'm back at my desk, I might even do a bit of digging around because that's interesting. So thank you for that.
Okay, thanks. Yeah, okay.
All right, so we got a couple other questions, and we got 2 minutes. So we're gonna, Peter Luchak, he's not on audio, so I can't unmute him, but he had asked a similar question about the sizing. And so maybe you already answered this, I'm not sure, but he mentioned that, you know, he's got a 9.5 inch distance between shaft ends, and let's say a 3.5 inch shaft. He's just wondering if that's enough space to put in a Torquetronic system.
Yes, it is, but there are caveats because it depends on how much twist is in that length, and that depends on how much power is coming through and what the shaft's made of. You know, if it's titanium, it will twist more. So again, if you want to send me the shaft to have a look at, I can give you some exact answers. Typically for a phase shift device, for Torquetronic's phase shift device, the longer the better because there's more flexibility. But we've done down at, it was DuPont at the time, we've got 5.25 inch DBSE with our Torquetronic on it.
Wow. Okay.
So you know, it can be done. So
definitely application specific. We got to look at it case by case. Ryan Marks has a question again. He was asking about the prototype, the laser, and just wondering why it hasn't gone past the prototype phase. And you know,
because nobody would try it.
Or the reason for going that way. I guess what would be the advantage of going to that? Accuracy, I'm guessing.
Well, to be honest, for Torquetronic, it's a bit of a double-edged sword because that was designed to look at torsional vibration basically, and it was designed to be cheap. We wanted it to be low cost, and that's why. So lots of the components are available from, you know, your local electrical wholesaler, and we had the slotted discs made by a local engineering company to give us the accuracy, and it was designed so that it would replace the shims in a coupling configuration. So you take a 2mm shim out and you put one of our slotted discs in. And so we prototyped it in the laboratory. We got some readings that made some sense, but then it's then going on and saying, okay, what do we do with it now? You know, we can't sell it. You know, we don't have a electric motor driving a pump or a compressor in our backyard. And it's very difficult. And you know, we are a relatively small company in the middle of the UK, and there are very few opportunities to give people toys to play with these days, and it's a shame. But it was very promising. And if anybody says, look, well, we've got this test facility here, why don't you chuck it on that? Then I would be, well, I wouldn't go on a plane tomorrow because I can't fly, but you know what I mean? We would embrace that and love you forever almost, because that's the sort of thing that gives us good feedback as to whether it actually is a goer or not. Yeah. So it's on our drawing board, still sat there.
Well, Ryan's unmuted, so you know, if you want to add anything, feel free to. But in the meantime, you know, we're going to wrap this up fairly shortly. And I was doing some digging and I actually noticed, and I put it on the screen now, that actually we did mention some torsional stuff at our 2018 MRO. So all that stuff is, you know, available on the archives on our website. So, you know, for anybody that's not aware or familiar, there's a lot of stuff you can search through. And
yeah, and Bob knows his stuff. Yeah. Bob certainly knows his stuff.
You know him, okay. Small world. Okay, yeah. Well, if there's no other questions, you know, hey, we're gonna send some stuff, or we're gonna post some things up on LinkedIn, some downloadable content. Feel free to carry on the conversation there, or send us an email, and we'll go from there. So thanks very much, and we'll see you next month with Burkhardt.
And thank you guys.
Thank you. Bye-bye.
Bye.
Bye all.
Bye-bye.